Hello there, this is Douglas Rumbaugh, and welcome to the first video in a short series of videos which I will be doing on the topic of pointers in the C and also C++ programming languages. So what exactly is a pointer? Well, easy. A pointer is nothing more than a memory address. That's all there is to it. So thank you for watching. Don't forget to like and subscribe, and I will see you in the next one. Well, not really. There's still a lot more to talk about here because although in principle the definition of a pointer as a memory address is really simple, it still is quite complicated. Not because pointers themselves are complicated, it's just a number, it's just a memory address. But rather because all of the other information that is wrapped up in what any of this actually means. So I want to take a minute and describe the surrounding content around pointers, and then we'll look at some of the basic syntax for using them. So going into this, there's a couple of prerequisites that I'm going to assume that you have. I'm going to assume that you know a little bit about basic programming. You know what if statements are, loops are, functions are, you know about variable scope, things like that. Doesn't necessarily have to be C. C is sort of the ancestor of the majority of modern programming languages. So if you're familiar with any programming language, you'll be comfortable enough in C with the exception of the pointers, which is what we're going to be talking about. So that works out pretty well. You also need basic hardware knowledge, know what a hard drive is and know what RAM is, that sort of thing. And we're going to be using Linux, so basic Linux knowledge, particularly user-level command line stuff, is also going to be helpful. Beyond that, I will be introducing all the additional concepts as necessary, and we're going to take this somewhat iteratively. There is quite a lot of stuff behind the curtain, and to just fling it open all at once would perhaps be a little bit overwhelming. So I'm going to try and be a little incremental with my approach here. Ultimately, at the end of all of this, we should have a fairly good understanding of not just pointers in C, but also some fundamental systems and operating system level content. All of the example code that we will be using throughout this series is available in a public Git repository. URL is right here. If you have no idea what the hell Git is, don't worry, I'll demonstrate pulling it down. It's just a couple of commands. Okay, so let's get right into this. I'm going to go ahead and make a directory to use for all of this, and we'll go ahead and clone down my repository. You should be able to execute these commands exactly as is and get the code that you need. And then we'll check out my episode 1 branch and take a look at what we got. Now, real quick, for those of you who may not be super familiar with C or how it works, C is a compiled programming language, which means you cannot go directly from source code file to program execution. There's an intermediate step. You have to compile the code into an executable binary first, and then run it. So, just in the interest of completeness, GCC is a perfectly good compiler. The GNU C compiler, it's GNU C compiler, but it's been retroactively renamed the GNU compiler collection because it does more than just C. Anyway, if you just run GCC and then the name of your C source code file, it will drop this a.out, and then you can run a.out. So we have compiled hello world, and now we simply need to execute a.out, and we should see the text hello world on the screen. I'll be right back. Okay, well, thanks to the magic of editing, we are back. Let's try this again. Hey, hello world. Okay, great. So that is how you run a C program. But what actually happens when you run a C program? This is actually going to be surprisingly important for understanding a lot of how all of this stuff works. It's peeling back the hood just a little bit. Now, I'm not going to get into the details of how any of this works just yet, but effectively what happens when you run the program is the operating system is going to create what's called a process. This is something you're probably familiar with. You have a PS, gives you a process listing and you have PIDs and all of that, right? So this should be old hat if you're familiar with Linux user space. And this process abstraction is used to represent a running program. And associated with the process are a bunch of pieces of information and a bunch of data contained within the operating system itself, contained within what we would call the kernel. Now, one of the most important things that is associated with a process is its memory. As you're probably aware, memory in your computer is where data actually gets stored. And additionally, because we are running computers that are based on a von Neumann architecture, the instructions and data are stored together in the same spot. So our process's memory space is going to contain both the data within the program, that's all your variables and things like that, and also the source code. So if we're going to get a handle on this, especially since, as we just said, pointers are memory addresses, if we're going to get a handle on all of this, we need to take a look at what this memory actually looks like. A good way of conceptualizing memory is as a sequence of buckets into which data is placed. Now, memory on at least Intel platforms, Intel x86 and whatnot, which is what I'm using right here, x86-64, memory is byte addressable, which means that each of these little buckets has a size of 1 byte, that is 8 bits. So it'll store 1 character, for example, 1 letter. Now, notably, the memory addresses that we work with in our C programming land are actually what are called virtual addresses as opposed to physical addresses. So imagine you have 16 gigabytes of memory in your computer. Well, each byte of those 16 gigabytes is going to have associated with it a number, a physical address, starting at 0 and running up to 16 billion. To access a piece of data stored in one of those bytes, you simply access it by address. The problem, of course, is that this is really unwieldy for partitioning that address space of 0 to 16 billion up between different processes on the computer. So what we do nowadays is we use what's called virtual memory in order to make each process think that it has its own isolated memory space. And this memory space runs from address 0 at the bottom all the way up to whatever the maximum addressable memory size is on our architecture. So, for example, in Intel x86, it's a 64-bit system. It uses 48-bit memory addresses, which means that the memory address space has 2 to the 48 addresses in it. And so we can address a ton of memory that way. We'll get into the details of how that works later. But remember, each individual process sees virtual addresses from 0 up to 2 to the 48 minus 1. So in each process, in 2 different processes, accessing the same virtual address will actually get different physical memory for the most part. There are a couple little exceptions there, but for the most part. So that's why I say virtual address here. Now, when we're looking at memory, it's actually, particularly when we're talking about the sorts of things that we will be talking about in this series, this sort of diagram laid out horizontally like this is actually not usually how it's done. This is how I do it in, say, my introductory Python programming classes and things like that. But for us, we're actually going to look at memory stacked up like this, where we have the high address is at the top and the low address is down here at the bottom. So 0 is at the very bottom, and in this case, F. These are hexadecimal digits. Memory addresses are usually represented in hex, so I'm just using hex here. If you have no idea what that means, don't worry. It's not super relevant right now. We'll talk about it. So you go from 0 at the bottom all the way up to whatever your maximum memory address is at the top. And because this is virtual, for reasons we will talk about when we get to paging later, the virtual address space that you see is significantly larger than the actual physical memory that you have installed. It's a little complicated. Again, we'll dig into the details of that later. It's not super relevant right now. Now, this entire virtual address space that your program has access to is going to be partitioned up into different chunks, which are responsible for storing different things. So for our purposes right now, as a simplified example, we're going to look at something like this. So again, imagine we have 0 down here and 2 to the 48 minus 1 up here. These are high addresses. These are your low addresses. This is a very partial map. There's a lot of holes in it. We're looking at like a Renaissance era map of the world here. There be dragons, right? But if we ignore the red bits, which we'll fill in later, there are 2 significant sections for us right now. And those are text, which is traditionally located at the bottom, although as we'll see later, this isn't strictly true anymore, but we'll still use this standardized diagram to talk about it anyway. Text, which is stored at the bottom of your low address space, and then the stack, which is stored right here, which is significant for tracking function calls and local variables and things like that. Those all get stored in the stack. So the operating system is going to prepare this address space for your program. Text is where the actual executable code goes. So remember that a program is just a sequence of instructions. Those instructions are stuck right here. Whenever the program goes to execute, there are 2 things that are done. The first is one of those instructions in text is selected as the first one to execute. That is what's known as the entry point. And so that's going to get loaded up in the appropriate way. And additionally, we're going to get what's called a stack frame, which I'll talk about in just a second, pushed onto the quote-unquote top of the stack. And this stack frame is going to represent your main function. So in C, you have a function called main, which is your entry point, and you start, the code will execute from the top of the main function going down. Now, one thing to note about the stack is it's a stack, which means you push things on top of it and pop them off the top, is the stack actually grows downwards from high address to low address. So as we grow the stack, as the stack gets bigger by a mechanism we'll talk about just next, your addresses are going to actually decrease. That's can be a little bit tricky to think about, although 99.999% of the time, it's not something you have to worry about. Now, what is this stack actually used for? Well, the stack is used to keep track of function calls and their local variables. So what's going to happen is if our program, this is what it looks like initially, and as it's executing, say it calls a function. Well, what's going to happen is we're going to create, well, we won't, the computer will create what's called a stack frame. And the stack frame consists of some identifying information about where you are and where you're going, things like that, as well as space for all of the local variables inside of the function. It's going to take those and it's going to push them onto the stack. Now, that's going to result in something looking like this, where again, remember that the stack grows downwards, so the top of the stack is actually at the bottom. So our current function is sitting at the top of the stack, and we have main below it. Now, when this function returns and completes, what's going to happen is its associated stack frame is going to get popped off of the stack, just like that. So you can imagine if we have multiple function calls deep, we'll have a bunch of these stack frames stacked on top of each other. And then as they return, they'll get popped off and we'll get back to the main. I hope that makes some semblance of sense. Now, the stack frame itself, it's worth noting, if we go all the way back to here, that we are still talking about bytes with associated virtual addresses. So if we roll all the way through here and zoom in on the stack frame, for example, here we have a variable int a and a double pi. And so if we look at the way the stack frame is arranged, we'll see there's some red stuff that we're not going to talk about at the moment. But if we pretend that this starts at virtual address 101, and again, well, actually, I have it numbered backwards. I'm sorry. This should be 110 going down to 101, but you get the idea. What's going to happen is our integer a is going to refer to these 4 bytes of memory. So on like a 64-bit machine, an int is going to be a 32-bit integer, takes up 4 bytes. And so you can see there are 4 of these addresses that are associated with the A, whereas the double takes up 8 bytes. And so there are 8 addresses that are associated with it right there. Okay, so what does any of this have to do with actual pointers? Well, let's take a look, first of all, at just using a pointer to begin with. So remember that a pointer is fundamentally just a memory address. So if we take a look here, we have int x equals 4. Now this is creating just an integer on the stack. So this. And inside of these bytes are going to be the binary representation of the number 4 in this case. So that's all we're doing there. It's worth noting, actually, this is probably important to note, that this literally contains the number 4, these bytes here that are allocated to the variable. The number 4 is literally here. This is not like a reference type language like in Python, where every variable simply contains the location of the data, which is stored somewhere else. In C, everything is a value type, which means that the data is stored directly in the bytes that are allocated to the variable. So the bytes 101 through 104 containing the associated with the variable a, or x in this case, is going to literally contain the binary digits representing the number 4. Now, what we're doing here is we're declaring and defining a pointer to an integer. So the way that you do this in C is you simply say the data type that you want a pointer to, you give the name of your pointer, and you put a star between it, just like this. Syntactically, you can do it like this with the star attached to the data type, or like this with the star attached to the pointer name. Both of those are perfectly fine. So this is declaring a pointer. Now, when we actually define the pointer right here, you can see I say x like this, and I give an ampersand. The ampersand means get the address up. So if we pop back over here, if we're looking at this guy and we pretend to say is actually x, then 101 would be the address of x. So the x itself is going to contain the number 4, but the address of x is 101, the address of the beginning of the variable in memory. So we are effectively, if we're using this stack frame as our example, we are storing 101 inside of this pointer. All right. And so then I'm just going to print and display both the pointer value itself. So this is the literal memory address. And then here, when we say the star again, this is what's called dereferencing. This is going to follow the pointer to the source data and get its value. So we'll see what that looks like. Okay, so if we take a look at this, again, x's value is 4. So we see a 4 when we dereference the pointer to x. And this right here is the memory address. Notice it is a very big number because, as we said before, our stack is located up here in the high address space. So our stack pointers are going to have, or pointers to data in the stack rather, are going to have fairly large values. Now, as a slightly more complicated example, let's look at an example with a function call. Now, ignore these warnings. I'm just not casting. Well, so what we're looking at here is, again, we still have that int x and pointer x, whatever. And then I call a function right down here. And inside this function, I have 2 more variables, and then 2 more pointers to those variables, and I print out the pointer values. So we should see the location of x followed by I followed by d, basically. So let's go ahead and compile this thing and run it. Now, we notice that, like I said, x is in main, and then a and p are in the function, right? So that would be analogous to this situation. X is going to be up here, and then a and pi are down here inside the actual stack frame for the function. And we can see that in fact bears out x has a larger memory address than a and pi, because x is closer to the high address than a and pi are. So that makes sense. And if we take a look, you can see there's a big gap between x and a because they're in different stack frames. However, if we look at a and pi, you can see they're back to back. A is at 868 and then 4 bytes later, pi picks up at 872. If we declared another variable after pi, it would most likely be located at 87a, right? 8 more than that. So that is what a pointer is. It is nothing more than a memory address, and I hope that in this episode I was able to demonstrate precisely what that actually means, what the memory address actually is. Now, in the next episode, we're going to take a look at actually using these pointers to do things, and in the process, we will have to fill in some more of that empty map. So I hope that you found this video interesting and useful. As always, leave any questions or comments in the section down below, and I will see you in the next episode.